My name is Boris Sokolov. I'm a research fellow in the Laboratory for Comparative Social Research. So, a few introductory words about the content of my course and some supplementary materials. So, this course is intended to cover 5 general topics in the context of structural equation modeling. The first and the most basic topic is confirmatory factor analysis. I will not discuss explorative factor analysis. I assume that most of you are familiar with this method. And actually, explorative factor analysis is not a part of structural equation modeling. Then we will discuss a subfield of factor analysis, which is known as multi-group factor analysis, which is of primary interest for comparative research. Then we will discuss structural equation models, the basics of structural equations. Then we will discuss an extension of the basic SAM, so the so-called causal analysis in the context of structural equations. And finally, we will discuss throughout the course various aspects of practical implementations of SAM in different programming software. In particular, we will use 2 general packages. The first one is R and the second is M+. Few words about recommended readings. There are a lot of brilliant textbooks devoted to structural equation modeling, but most of these textbooks are not available for free. I was able to find only one textbook in free access. It is a book by Tim Brown, published in 2006, which is called Confirmatory Factor Analysis for Applied Research. And it is one of the most cited textbooks on the topic, so I think that it will be a good help for you for learning structural equation modeling. Our everyday schedule will consist of 3 sessions. During the first session, I will discuss various theoretical aspects of structural equation modeling. Then, during the second session, we will apply this theoretical stuff using some practical examples. And finally, I assume that during the third session, you will try to apply new methods that you have learned during the previous 2 sessions to your own research problems. It's not obligatory, but for my belief, I think that only personal experience with new techniques can allow you to learn these techniques well. So I would strongly recommend you to apply all methods that we will discuss to your own research problems. As far as I know, all of you will send an email in which basic requirements to the datasets, which will be useful during the course will listed. But nevertheless, I also repeat these requirements in the end of this first section. And finally, all course materials, all readings that I will cite, all replication codes, all datasets will be available, and in the Dropbox folder I will share with all of you this folder after the session. And the final remark, first of all, my English is not very well, and some topics are really difficult. I will not use a lot of math during the course, but nevertheless some stuff is difficult, so if you understand that you don't realize what's going on, please do not hesitate to stop me and to ask what is it. Okay? So, let's start. The structural equation modeling is actually a combination of 2 different fields of statistics. The first field is the well-known regression analysis, and I think that all of you know what regression is. And the second crucial component of structural question modeling is latent variable modeling. So it's useful to start with the concept of latent variable. Probably most of you have heard this term, latent variable. And now let's try to define what is latent variable. Who can try to say a few words about his or her own understanding? What is latent variable?
A variable that cannot be directly measured, but can represent itself in its manifestations, which we can measure. Several manifestations.
Okay, can you give an example of latent variable?
For example, religiosity is a latent variable. It consists of a number of dimensions, like attending church services, praying, believing in God, or believing in some other entities. All of these are measurable manifestations of an inner latent variable which cannot be seen directly. We don't have an instrument to measure it directly.
Yes, religiosity is a good example. Actually, we cannot observe directly how a religious person is, but we can look at different manifestations of religiosity. As Yana said, this can be the frequency of attending church services, believing in God, or maybe in hell, and some other aspects of religious behavior. And combining together the different performances on these particular indicators can give us more information about how religious person is, right? Let's try to give another example of latent variable.
Any linear combination of absolute variables would be a latent variable.
But I would like to get an example with some concrete sense, like religiosity, because your definition is too abstract, and we need to fill this definition by some concrete sense, like religiosity, or another example of latent variable. Sorry?
Okay, just your everyday behavior might be dependent by multiple factors. You do not observe them, and you want to explain some the influence of your attitude on, for example, your economic performance, on your income, or something like this. And you see that there is no link, but you feel that it should be that your attitude definitely determines your income. And to reopen this concept, your attitude, you add additional variables which can explain your attitude, and which might as well influence your income, like the environment you were grown up in, your family's religiosity, your education, the country you live in, the values of the country, of your political culture, and all these things. They can influence your everyday behavior, which can influence your income. But there is no direct link between the variables.
Sorry, but I don't agree with your example. You say about causality. You simply list different sources of different factors which can affect your income, right? But I don't think why we need to involve a concept of latent variable in studying different determinants of income. I would give another example of latent variable, probably the most basic example. It's IQ coefficient. There are different aspects of intelligence in human heads, right? Some people perform well on counting, others perform well on reading, and so on. And we cannot determine directly which is the IQ of any single person. we need to give a variety of tests, and the average of all these tests will give us an approximation of the power of personal intelligence, right? So, latent variable is not only a broad concept that can be measured using different variables. Latent variable is a, how to say it, okay, let's start from another side. Let's start from theory. I think that science, and in particular social sciences, is an enterprise which is intended to test different theories using real data. What is the basic component of any theory? It is a concept. Each theory implies several concepts, and we try to operationalize these concepts using some absurd variables. In many practical instances, we can directly measure these concepts, but in many other instances, we cannot do it. So here we need to introduce latent variables. Formally, we can define a latent variable, or term factor is often used in psychology and sociology, so that's why it's called factor analysis. We need to introduce latent variables when we cannot directly observe our concept or construct, as it's called again in psychometric theory. And actually, latent variable is an absurd factor responsible for variation in a set of different absurd indicators, which are meaningfully related with each other. And when we use latent variables to measure some unobserved constructs, that's called a measurement model. That's the first part of any structural model. Another part of structural model is so-called regression part or structural component. So in general, as I already said, structural question modeling is a combination of two components. First component is a measurement model or a latent variable component, and another component is a counterpart of simple regression. But in the context of SEM, we can combine regressions and measurements. Just to give you a formal example. Again, we can use the example of with religiosity as a latent variable. And what is the nature of relationships between latent variable and absurd variables? Imagine that we have 5 absurd indicators of religiosity. We can give different names to them. Frequency of attending church services, believing in hell, believing in God, and some other. Frequency of praying, and so on. In the context of latent variable modeling, we assume that a latent variable, which is called, for example, religiosity, affect variation in absurd indicators and also correlation between these indicators. What is essential is that the latent variable is a cause of variation in absurd variables. Actually, it's not always the case. We can imagine another situation when actually the latent variable, the absurd construct, can be affected by variation in absurd indicators. So that's a basic difference which is useful to distinguish between latent variable modeling and, for example, formative constructs. The direction of causality, the direction of relationship between latent variable and absurd indicators. When arrows which link latent variable and absurd variables directed from factor 2 indicators, we can say about factor model or latent variable model. But where these arrows are directed to from indicators to construct, this kind of model is called formative model. Just to give you an example, Human Development Index. Who know how it is computed?
Life expectancy and GDP and something about education.
Yes, it involves many components like GDP and so on. But what is essential, you cannot compute HDE for some given country if you don't have an information about the level of GDP for this given country. Even you have scores for all other components of HDI, you cannot recover the general score without information on at least one component of HDI. So all components are essential for computing the general score on HDI. But in latent variable modeling, all indicators are assumed to be an interchangeable manifestations of the latent variable. So if you have actually 5 indicators, you can skip one indicator from the model, and nevertheless you can still recover the score on the latent variable. That's the key difference between formative models and latent variable models. Again, just to repeat, the most simple and visual tool to understand the difference is the directionality of these arrows. More formal way to distinguish between formative models and latent variable models. Both involve multiple indicators related to some meaningful and theoretically loaded concept. In formative models, all indicators are important, and skipping one of these indicators lead to impossibility to compute the general score. But in latent variable models, all indicators are interchangeable. So, what kind of information, of statistical information, we can use when we deal with some observable or latent variables? The only available piece of information is so-called variance-covariance matrix between relevant indicators, which we assume to be related to the latent variable. In the context of factor analysis, it is assumed that any variation and correlation in observed indicators is conditional on the level of latent variable. We can, for example, observe a correlation between two indicators of religiosity as high of 0.9, for example, believing in hell and believing in God. But it does not mean that believing in God determines the level of believing in hell, and vice versa. It does not determine that the level of believing in hell determines the individual level of believing in God. It simply means that we can explain this high correlation with referring to latent concepts of religiosity. And when we account for this latent factor in our model, the observed correlation between these two indicators, believing in God and believing in hell, should disappear. And the general purpose of factor analysis is to find such solution which will approximate the observed variance-covariance matrix of relevant indicators as best as possible. So, in other words, factor analysis is, as any statistical procedure, is a maximization problem. But what we try to maximize, or in other words to minimize, is a discrepancy between the observed variance covariance matrix of some theoretically loaded indicators and of the variance covariance matrix which are predicted by our theoretical model. Here you can see the so-called general or common factor model, which is quite similar to basic regression model. And what we have, which components are included in this equation. In the left part, you can see a kind of dependent variable, yg. Yg represents the value of g's among p. P is a general number of indicators which are included in our model. So yg represents the g's indicators or manifest variable. Both terms are synonyms. And in the right part, you see a combination of products of two elements: lambda with some lower indices and eta with some lower indices. In the theory of latent variable modeling, eta is a convention notation for latent variables, and lambda is a counterpart of beta coefficient in simple regression setting. So actually, in latent variable modeling, we try to relate observed indicators and latent variables using multivariate regression. We have the difference between regression and factor analysis is that we have only one dependent variable in any regression model, but in a factor model we have multiple. Yes.
Yeah, sorry. The question is about the intercept that is usually present in the regression model, and it is absent only if the solution is standardized, right? So in this particular formulation, there is no intercept. So I wanted to ask a question about it.
Yes, we can include an intercept, but here the model is given in standardized form. And actually, I will say a few words about that later. In one group setting, in factor analysis, intercepts are not useful, so we can simply skip them from the model. So, just to repeat. In factor model, we have many dependent variables, which are our observed indicators or manifest variables, and we try to predict them using the variation in unobserved variables. Generally, we may have as much latent variables as the number of observed indicators in our model. So in the general setting, we can have multiple latent variables related to one observed indicator. And the measure of strength of relationship between our latent variables and our observed indicators, which is called the factor loading, is denoted by lowercase Greek letter lambda. A few words about indices. G is the index for observed indicators. For example, using our example of religiosity, believing in God is the first indicator, believing in hell is the second indicator, frequency of praying is the third indicator, frequency of church attendance is the fourth indicator, and so on. And another index, 1, 2, 3, and so on, is the index for latent variables. So if we have several latent variables related to one indicator, we will have as much factor loadings as a product of the number of latent variables in the model and the number of observed indicators in the model. And as in any regression, we have error term, which allows us to account for measurement error presented in the model. In matrix form, we can express the latent variable model in a very simple equation, which involve 4 vectors: the vector of absurd indicator, the matrix of factor loadings, the vector of latent variables, and the vector of residual variances or error terms. And in the expanded matrix form, we can express any latent variable model using the following notation. Uppercase sigma is a p by p symmetric correlation matrix of our indicators. Uppercase lambda is a p multiplied by m. I recall you, p is the number of absurd indicators in the model, m is the number of latent variables in the model. So uppercase lambda is a p by m matrix of factor loadings.
In English they say psi
Psi.
instead of psi.
Psi is a m by m symmetric correlation matrix of the factor of the latent variables. They can also, in general, correlate between each other. And finally, theta is a p by p diagonal matrix of error terms, so unique variances in the model. Actually, it's not necessary to understand the basic principle of latent variable modeling, but Ken Bolen said me that he's going to use some matrix algebra, so I present it for you. Which are the basic concepts which are used in the general factor model? I already said that factor loading is a counterpart of regression coefficient, beta coefficient in regression, and we can understand factor loadings as the partial correlation coefficients between the observed indicators and latent variables. The squared factor loading can be understood as an approximation of R squared for each particular indicator in the model. So if in the regression we have one R squared, in factor analysis we have multiple R squared, one for each absurd variable in the model. Then, communality. Communality is the sum of the squared factor loadings for all factors for a given variable. It is a variance in that variable accounted for by all the factors. It can be also understood as a counterpart of R squared, and in the context of the general factor model, maybe it's a better approximation of R squared than squared factor loading, but because we will deal mostly with confirmatory factor analysis, which implies that one indicator can be related only to one latent variable. Both these quantities, I mean squared factor loading and the sum of squared factor loadings for all latent variables, can be used as an approximation for R squared for absurd indicators. The uniqueness is the variability of indicator minus its communality. So we take the variance of any absurd indicator, then we subtract the sum of squared factor loadings for all latent variables related to this indicator, and thus we get the amount of unexplained variance in our indicator. Then eigenvalue. Eigenvalue is the sum of squared factor loadings for a factor. So it's an important difference. Both communality and eigenvalue is the sum of squared factor loadings. But the index for when we compute communality, we index by factors. So we take one indicator, we take all factors related to this indicator, and we compute the sum of squared factor loadings for all of these indicators. When we so communality is related to indicators. eigenvalues are related to latent variables. So eigenvalue is a sum of squared factor loadings for some particular latent variable in our model. And it can be used as an indicator of predictive power of latent variable compared to other latent variables. And finally, factor score is approximation of, because we actually do not observe the scale on which latent variable is measured, but if we try to use this in our model, we need an approximation. So we need to find some concrete number, some concrete score, which can be used to, for example, to create ranking of all individuals in our sample on the latent dimension. So factor scores is a score of each individual on some particular latent variable. It can be computed in different ways. For example, we cannot, we may not use any factor models. We can simply use sum scores on all indicators which we assume which are assumed to be related to latent construct. And the main advantage of latent variable models is that they account for measurement error, because different indicators can be related to the latent dimension with different strengths. And when we use sum scores, we assume that the relationship between each indicator and the latent construct is the same for any indicator in our model. But it is actually not the case, and the factor models allows us to account for this measurement error, for difference in the strength of relationship between particular indicators and the latent variable. Again, I have said that I will not discuss the issues related to exploratory factor analysis. Maybe for some of you this technique is known as principal component analysis, or by some different name. But why? Why I will not focus on exploratory analysis? So what's the difference between these two methods? Exploratory factor analysis, actually, it's a kind of data mining procedures. It is designed for preliminary exploration of observed data, for dimensionality reduction of observed data. For example, we have 100 survey questions, and probably we do not have any expectation about latent dimensions behind these questions. And we can try to explore this data by using EFA. And the goal of applying EFA is to maximize an amount of explained variance and covariance of observed indicators. My strong belief is that we should have a theory when we start to work with data. And CFA has a great advantage over EFA, because CFA is a confirmatory procedure. Using CFA, we try to test our theory against the data. We don't simply explore our data. We don't simply mine our data. We have a strong theory, which have some clear implications, and then we use CFA to test these implications against the data. So CFA is a theory-driven approach. One formal difference between these two methods. Because if we try to maximize the amount of explained variance in observed indicators, it estimates all possible factor loadings. For example, we have the same 5 indicators, and we found that 2 factors can explain a large amount of variance, but in this model we assume that each indicator related to each factor. So we have, for example, in this case we have 10 factor loadings. In C-phase setting, we, because we use some theory to make some predictions about the latent structure, we, for example, again have the same two factors, but, for example, our theory assumes that first two indicators related on to the first factor, and the next three indicators relate this.
When you finished about this, I would like to keep you this slide and ask a question about a previous slide.
Okay. So, and the next three indicators are related to the second factor. But these three indicators, we don't assume that they are related to the first factor. And vice versa, we do not assume that these two indicators are related to this factor. So, because our theory implies this structure, we can test whether this structure, for example, matches this than this structure. And you see that this model is more parsimonious, and it helps us to follow the famous Occam-Razor principle. If we can explain the observed operation in observed indicators with only 5 quantities, it is not necessary to involve other quantities.
Is it not possible, or it is not advisable not to have a factor influencing?
It is not advisable. You can explain the same variance covariance matrix in a more parsimonious way. And if this explanation is plausible according to some statistical criteria, it is not necessary to use a more complicated explanation. And in addition, this explanation can be seen as the test of some theory, but this model, this explanation will involve a need in creating some new theory. So that's the difference. Here, you start from theory and then use data to verify or to reject the theory, and here you start with data and then you invent some explanation post hoc. So what do we...
No, please keep this slide. So I have a question about that slide where there were a few definitions about commonality, uniqueness, and this sort of thing. So, and eigenvalue in particular. So my question is primarily about eigenvalue, but I would like to use this picture to. So if we square this, assuming this is a standardized solution, so this is a partial correlation, right? And then when we square it, it's sort of how much of the variance of y1 is explained by this factor.
Right.
When we square both of these, right, then we have how much variance is explained by this factor in the two variables,
Yes.
right? And so the same, so this is like partial r square, in a sense.
Yes, it's a partial r square for certain indicators.
Right.
But probably it would be better to explain this concept using this figure.
Okay. But to continue, uniqueness is again assuming that the variance of this is 1, that is, it is a standardized variable, is 1 minus lambda square, right?
Right.
So this is uniqueness.
Yes.
And commonality is?
The commonality is here the uniqueness, the commonality coincides with r squared because we have
Right.
only one factor accounting for the
Right.
relation in this
So
variable.
if we had another arrow from factor 2 to y1, then we would have this lambda square and this lambda square, and the uniqueness would be smaller because there would be two factors explaining y1,
Yes.
right?
Yes.
So, and of course the r square explained in y1 would be higher. Okay, but then can you explain eigenvalue here?
for example, factor 1, it has 5 arrows directed to certain indicators, and thus it has 5 meaningful factor loadings, lambda 1, 1, 1, 2, and so on. So the sum of squares of all these factor loadings will give us an eigenvalue for the factor 1.
So when we calculate eigenvalue, we concentrate on factor rather than on
Yes.
on the indicator.
Yes.
Thank you.
Formal advantages of CFA over exploratory factor analysis. For me, the most important advantage of CFA is that it is a theory-driven procedure. But it is a substantial advantage. CFA also has some technical advantage. First of all, it allows for the specification of additional model parameters or constraints imposed on these parameters. For example, let's go to the previous slide. You see that here we have 10 factor loadings, and each factor is related to each indicator. In the basic CFA model, we have no such additional parameters. Generally, they all are assumed to be zeros, but if needed, we can add these parameters. For example, we can find that these indicators correlates not only with the first factor as we assume initially, but also with factor 2. And we can test whether this additional correlation is significant. Here we simply estimate all possible correlations in the model between latent variables and observed indicators. Here we can test for meaningfulness of adding this additional parameters in the model. And also we can test, for example, whether these partial correlations are the same, whether they are equal. If we can simply estimate them, and we cannot do nothing more. Then, in the context of EFA, we have no criteria of model fit. So we simply try to maximize the amount of explained variance and covariance in observed indicators. But in CFA, we can directly assess whether our model is good or bad. Then, in the context of comparative research, it's important that our models have the same meaning in different populations. For example, we can again continue with religiosity. In different religions, different aspects of religious behavior can be seen as important. And if we try to develop a comparable measure of religiosity, which will be applicable among Christians, among Muslims, and among the representatives of any other religions, we need to ensure that our indicators are interpreted in these different religions in the same way. And again, in the context of EFA, we cannot test formally this assumption of comparability, which is also known as the assumption of measurement equivalence. But in the context of CFA, we can. Further, in the context of CFA, we can introduce a measurement error in our model. And finally, CFA can be combined with regression. This combination is called SEM, or structural equation models. So we can directly assess the relationships of our latent variables with some other variables, whether latent or directly observed. In the context of EFA, we cannot do that. Now let's turn to particular CFA model. Previously, I have shown you the common factor model, common mathematical notation which can be used both for exploratory and confirmatory models, but confirmatory factor analysis notation may be a little bit different from the general notation. Again, the key parameter in the model is the factor loading. It has the same meaning as for common factor model. It is a correlation coefficient which expresses the strength of relationships between latent variable and observed indicators. Another key parameter is factor variances and covariances. Latent variables also can correlate with each other. And these parameters are denoted by phi, it is the right pronunciation, or phi, by Greek letter phi. And finally, the third kind of key parameters in the confirmatory factor model is the error variances and covariances. Error variances is a counterpart of commonality in the general factor model. It's the amount of unexplained variance in the observed indicators. And this unexplained variances may also vary between different indicators in some cases. Again, in the very basic setting, we do not assume that such residual covariances present in the model, but we can test for them formally. Now let me introduce the first empirical example. We'll work with this example during the first 3 days of our course. The example is based on the paper by Eldar Davidov, which we published in 2009 in Political Analysis, top-level political science journal, devoted mostly to methodological issues. The title of the paper is Measurement Equivalence of Nationalism and Constructive Patriotism in the ICCP, 34 countries in a comparative perspective. The paper is based on the International Social Survey Program. Probably some of you know what this program is. It's a large and cross-national survey project like World Value Survey, European Social Survey, European Value Study, and so on. And this program conducts surveys on different topics. Sometimes the topics are repeated after some time span. And in 2003, the main topic of the surveys conducted under the auspices of ICCP was national identity. 43 countries were covered. The sample size is more than 40,000. And Davidov suggested that national identity can be divided in 2 different components. The first component has a negative meaning. It is nationalism, and according to Davidov, nationalism can be measured by 2 items. The first item, the world would be a better place if people from other countries were more like the country of where the respondent lives in. And another question is, generally speaking, respondent's country is a better country than most other countries. So evidently these 2 items involve some negative comparisons between respondent's country and other countries, so we can call the latent variable related to these 2 items as nationalism or aggressive nationalism, aggressive component of national identity. But Davidov also suggested that there is another more positive component of national identity, which he called the constructive patriotism. And to measure constructive patriotism, he proposed to use 3 liker type items from the ICCP questionnaire. The first, all these items measure how proud the respondent is about some different aspects of living in his country. The first aspect is the way democracy works in his country. The second is how social security system does work. And the third is how this country fair and equal treatment treats all groups in society. And again, these three items does not involve negative comparisons between respondents' country and other countries. They actually measure respondents' attitudes toward different aspects of living in his country. So it is a positive component of national identity. That's visual representation of this model, two latent variables. The first is measured by 2 items, and the second is measured by 3 items. How do you think, how many parameters we have in this model?
It must be 5
There
or
are
7.
6 arrows shown on the slide, but maybe there are some more parameters.
Okay, which kinds of parameters we have basically in factor model, in confirmatory factor model? 3 types of parameters.
We have also error terms for measurement and instruction.
Okay,
Right.
which kinds of parameters we have? 3 types.
Like factor loadings.
The first is factor loadings. The second is
Disturbance.
the second is disturbances or errors, and the third one,
Correlations between vectors.
yes, it's variance and covariances between factors. So, how many factor loadings we have in this model?
2 are fixed problem.
So how much?
5, but maybe 2 are fixed. Oh yes, I suggested.
We'll discuss this issue later.
Okay, we have
we
5.
have 5 factor loadings in this model. 5 arrows relating factors and third indicators. 1, 2, 3, 4, 5. Okay, how many factor variances and covariances we have in this model?
3.
3. We have 2 factors. Each has its unique variance, and these factors are allowed to correlate between each other. This bidirectional arrow refers to the correlation between 2 factors, and variances are not shown, but they actually exist. 5 plus 3, 8. 8.
We know.
8 parameters. So we have already counted 8 parameters in the model, but we also have an error terms for each indicators. How many error terms present in the model?
5.
We have 5 indicators, 5
Right.
error terms. So basically we have 5 plus 3 plus 5. In sum, we have certain parameters in the model. And this figure verifies our computations. So here I visualize the standardized solution for this model. We see that, again, just to recall, factor loadings are partial correlation coefficients when they are standardized. How we should interpret partial correlations? We remember general rules of thumb for interpreting correlation coefficients. Which correlations are considered to be strong?
The rule of thumb is greater than 0.3.
Yeah.
But, yeah, but it's totally arbitrary. There may be various
Uh,
thresholds.
I would, in most textbooks I have read, there is a consensus that correlations higher than 0.3 can be considered as meaningful. But what does mean correlation about 0.3? How much variance we explain in the indicator?
Less than 10%.
Yes, 10%.
0.3 squared.
3 in square will give 0.9, so about 10%. And 10% is not a very large explained variance, right? So we can consider this correlation as meaningful, but it is not obvious. It's obviously not strong. And basically, correlations higher than 0.7 are considered to be strong because the correlation of 0.7 implies the amount of explained variance in the indicator as large as
Almost 0.5.
yes, almost 50%. And correlations higher than 0.5, which implies 25% of explained variance in the absolute indicators, are considered as moderate in their strength. So what we can say about this model? Whether all correlations are strong in the model.
I would say that the second one is not that strong. It's not that.
Yes, actually we have only two actually strong correlations. This and this one. Because they are equal to or higher than 0.7. But what we can say about other correlations? Whether are they too low to be considered as meaningless? Actually not. They are sufficiently high. They are all higher than 0.5. So we can say from that all indicators are significantly related to the respective latent variables. Maybe not such strong as we wish, but nevertheless, the model is meaningful. Then, the relative sizes of factor loadings between indicators related to the same construct are also may be important. What we can say in this context? If we consider the latent variable constructive patriotism, we will see that all factor loadings are about the same size. So the difference between the highest and the lowest is 0.05, which is negligible. But for the latent variable nationalism, we see that the difference in factor loading sizes is quite large, 0.25. So we can say that this item, one's country is better than most other countries, is more important for measuring this latent variable. This item also important, but this is important more. And this case can be illustrated, can illustrate the difference between using sum scores without accounting for different sizes. Please.
Excuse me, which one is more important?
The highest, this one. For example, if we...
Higher loadings and smaller uniqueness.
For example, many researchers, when they use multi-item constructs in their models, proceed in the following way. They simply assume that both items are equally important for measuring nationalism, and they compute the score on nationalism simply by combining the score on this item with the score on this item and then taking the average. But actually we see that this item is more important, so we can use this information to weight the scores into particular dimensions and then to combine a weighted and a less biased score on nationalism. So then, here you see that latent variances are equal to 1. Actually, it is a result of standardization. We can use different approaches to standardize our model, but the most popular is to fix the latent variances. If we, for example, if we would use non-standardized solution, they may have some other values. But this is not very important. The more important parameter is the correlation between two factors, and we see that it's quite strong. It's moderate, but it's meaningful. So we can say that both positive aspects of national identity and negative aspects of national identity are related to each other. So, and now a few words about your assignment for the after lunch session. Again, so as I had said, it's not obligatory, but I think it would be useful to all of you to try to do them. I would like that all of you, actually you can work in groups, but these groups should not be very large, maybe 2 or 3 persons. So I would like that all of you, either you will work individually or in group, choose a large cross-national survey data set. A few examples include World Value Survey, Eurobarometer, and so on. Actually, you can use any data, but it is important that this data includes some grouping variable. Maybe university is if you work with educational data, or maybe country region if you are region-based, and so on. Then choose any 2 or 3 groups presented in this survey. Countries, universities, and so on, but no more than 3. Then choose a theory which is close to your research interests. You can use actually any model presented in the literature, not as reference, or maybe you can use your own theory which you try to test in your research, and derive at least one, or better 2 or more latent variables from this theory. Also think about possible predictors of these latent variables. You can also assume that these latent variables are causally related to each other. It depends on your theory and your own preferences. Then, define a measurement model to these latent variables. I mean, select several indicators that can be used to measure these latent variables. And please prepare a short presentation which will cover following components of your project. First, some very, very short literature review, the basis for your model. Then the description of measurement model, that is latent variables that are included in the model, and items which are used to measure these latent variables. Then simple data description, the data set, and the counters that you have chosen. Item wordings, and it's not so important at this stage, but nevertheless it would be useful if you provide a list of variables that can be related to the latent variables in the model. For example, basic socio-demographic predictors like age, education, and so on, but think about possible directions of relationships between these socio-demographic variables and your latent constructs in the model. I also would recommend you to try to write a paper, but we have only limited time, so again, it's not obligatory, but it is a good way to learn a new terminology when you try to write it down on paper. Please.
I have a question. Why we should choose just 2 or 3 countries?
Because I wish so. You will understand it later during the study of our course. So, after the lunch, you have 1 hour for preparation of your presentations, and you see that there is a lot of listeners and participants of our summer school, so I think it would be impossible that all presented after the lunch, but those who want, I think they will have 5 to 7 minutes to present the projects, and then 5 minutes to get some feedback from me and from the audience. And so generally that's it for the first theoretical session. We have about 20 minutes for questions. Or if you have no questions, we can go to coffee break. Please.
If you allow me, may I use this time to summarize the lecture, maybe in 5 minutes, to underscore and emphasize the important moments from your lecture?
Yes, you're welcome.
Okay. So, very quickly. What Boris presented today was the basics of the conformatory factor analysis. Conformatory factor analysis is essentially an analysis of a variance-covariance matrix. In standardized form, it is basically a correlation matrix. So what we have is a simple, we can use y or x, doesn't matter, y. So imagine we have 3 variables and we observe correlations. Of course, the diagonal of the matrix is 1s. If it is variance-covariance matrix, these are variances, but this is not important. And here we have correlations. Now, the idea of the factor analysis is that these correlations are spurious. They are not real, right? Because, as Boris was saying, religiosity, that you believe in God does not necessarily cause your belief in hell, or the other way around. Rather, these correlations are spurious because they are explained by a common factor. There is a concept called religiosity, faith, that explains y1, y2, and y3. Right? And how do we derive this? Well, once we know these correlations, there are only 3 of them, we can sort of guess what these regression scores, or partial correlations, because regression coefficient is essentially a partial correlation when regression is standardized. When regression is standardized, the regression coefficient is a partial correlation. Right? So we have factor loadings, and when we square them, this means how much of the variance of y is explained by this common factor. How much variance of y2 is explained by this, lambda 2 squared and lambda 3 squared. If these variables are also standardized, their variances are 1. So why these correlations are not perfect? Because in addition to commonality of the common factor, there are also uniquenesses, right? If there were no uniquenesses, the correlation would be perfect. 1, 1, 1, right? But they are not perfect because there are additional factors. So this is religiosity, and this is some unidentified factor related to believing in hell. Maybe in some religions people believe in hell, and in some religions people do not believe in hell. Maybe this is why y1 does not correlate perfectly with y2, right? Because in addition to the common factor, there are also specific or unique factors, right?
And also measurement error.
True. Another component of the disturbance is not only the uniqueness, like people believe in certain religions in that, and in certain other religions that believe in something else, but also because there may be a measurement error, which is also a component of uniqueness. But this is, we cannot really distinguish between the two, not at least in this model. Right? So, so now we can calculate partial R squares, commonalities, and we also calculate uniquenesses, which is 1 minus lambda square 1, 1 minus lambda square 2, and so on and so on and so forth. But we also can calculate eigenvalue. The eigenvalue in this case would be also sum of lambda squared, but it will show the explanatory power of the factor. The explanatory power of the factor. If we had two factors, and let's say we have a loading here, let's call it for simplicity lambda 4, then the situation will be a little bit more complicated. Lambda 1 squared plus lambda 4 squared would give us the total variance explained in y1, right? So therefore the uniqueness of y1 will be smaller, because it will be 1 minus lambda squared 1 minus lambda squared 4. So this uniqueness will be smaller. And now we can distinguish between eigenvalue and commonality. Because when we concentrate on observed variables or indicators, we calculate commonalities, right? When we concentrate on factors and their explanatory power, we calculate eigenvalues.
So I would say that
So this is basically it. Yeah.
eigenvalue is a measure of how much variance we can explain by the factor. And commonality is a measure of how much variance we can explain in one indicator. So the difference in terms of variance in one indicator by all factors, and eigenvalue is the amount of explained variance by any specific factor in the model, in and by. So, good. Thank you for your
Can I
short.
ask a question?
Please.
If one of the indicators has very small variance itself, is there any limitations on the value of the variance that do not allow us to use this?
Maybe.
No,
It
one
depends
of the indicators,
Variance.
variance of the indicators is low.
First, it depends on the scale on which the indicator is measured. Some indicators may have very large means, but small variation around this mean. But if the indicator has a low standardized variance, it probably may lead to some estimation problem, but I have not seen any formal restrictions on the size of variance.
Rule of thumb? Any rules of thumb?
So if you have not variance at all in the indicator, you cannot explain anything, because there is nothing to explain. There is no variance. But if you have some small variance, you can determine whether it's enough or not only empirically. So you can test, you can try to include this indicator in the model, and if the software then returns you an error message, it means that this amount of variance is insufficient. But if software works well, so that's okay. Okay, any other questions? Please.
Could you please clarify when shall we make the decision to apply the the exploratory factor analysis instead of the CFA?
It's a matter of debate. I think that you should never apply exposure factor analysis. At least if you are a social scientist. If you, for example, data scientist, you can use EFA when you have a very large number of variables, and some practical instances you may have a need to reduce this number to some reasonable dimensions. So here you can use exploratory factor analysis, but in most applications in political science, which is the main domain of interest for me, or in sociology, you have only a limited number of observed variables, and you can make guesses about which latent dimensions related to these observed indicators, simply using, for example, item coordinates. Any item, for example, related to which includes the word religiosity, and so on, can be related to the latent construct religiosity, and so on.
And I have a question, why shouldn't I use it? Because just, for example, I'm just checking for dimensionality, and I find out that there's some variance, like due to different country-specific things. And then I should go back to exploratory factor analysis to see what might be the structure beneath and what makes for these very differences. I mean, just why shouldn't I? How else could I?
Yes, actually you can. It's a matter of taste. I think that you should have a good theory. And actually, probably no one initial guess can be perfect. And anyway, when you try to test your theory against data, you then face the necessity to modify your theory. But this modification, for me personally, also should be driven by theory. So yes, you can try some theory, then you can find that it's completely inappropriate. Okay, if you can, if you wish, you can use exploratory factor analysis to study the same set of items to find possible solution. But as my experience shows, if your confirmatory model does not fit well, I don't think that you will find a good exploratory solution using the same set of items. But again, it's my personal opinion. I wouldn't say that IFA is completely inappropriate tool. It has some advantages, and if you wish, you can use it. But I don't like exploratory factor analysis.
In structural equation model, when you use latent variable constructed by confirmatory factor analysis, you said that the score is not actually computed. It is not computed even in the program when it does the regression part, or it is computed but not shown to the user.
Actually, basically it's not computed because even in structural equation framework, you work with correlations, and you use correlations between variance covariance metrics of observed indicators, and then you relate these observed correlations to some other variables included in the structural model. But if you need to compute factor scores, you can cover them using some simple routines implemented in the most basic SAM software.
I have a question concerning the assignment. You say we should select 2 or 3 countries, right? So we fit a model for one country and fit a model for the second country, and what else?
So we start from fitting a model on the pool sample. On the pool sample. And since during the third day, we will try to fix separate models for each country. And then we will try to fit so-called multi-group factor analysis and test the equivalence measurement models between these 2 countries.
So we fit a model for both countries?
So first we fit a single model for both countries, and then we will try to fit separate models for each country.
And what we see?
You will see that during the third day.
Okay.
There is a very popular topic in comparative research which is called measurement invariance, and probably it's also would important for the second part of the summer school, because in latent curve models you have different time points. It also assumes that in each time point your measurement model has the same meaning. So the topic of measurement invariance, while it has its own meaning for comparative research, it can also be applied to the concept of latent growth curves, and that's why I decided to include this in the table for my course.
I see.
So we will try to establish the fact that the models for different possible subsamples, in my case countries or in other groups, and in the case of Professor Boylan for different time points, are the same. So that's a very basic explanation of what we will do. So, any other questions? So no questions, so we can go to coffee break.